Hello, everybody. Today we continue the topic dual and bidual spaces. So let me recall what we have already discussed last time. First, we have discussed theorem 6.3 that the canonical mapping, which is the mapping from X to its bidual, which maps any point X in this space big X, to a linear functional on the space X star, which acts as point evaluation exactly at the point X. So the statement is that this canonical mapping is a linear isometric embedding, and hence it is injective as an isometry, but it does not need to be surjective. And this leads to definition 6.6 that a Banach space is called reflexive if this canonical mapping is surjective, and hence, since it is both surjective and injective and isometry, it is an isometric isomorphism. And we also mentioned last time that there exist Banach spaces which are isometrically isomorphic to their bidual, but via some other isomorphism, the metrical isomorphism, not the canonical mapping. And it may happen that the canonical mapping itself is not surjective. So although we have this, so they are isometrically isomorphic, it does not imply that X is reflexive. For reflexivity, we need the isometrical isomorphism given by the canonical mapping. Okay. Also, last time we have mentioned that in the finite dimensional case, everything is always fine. That is, each norm space is closed and hence Banach space, and it is always reflexive, and dimension of X is equal to dimension of its dual and its bidual, and algebraical and topological dual coincide because all linear functionals are continuous in the finite dimensional case. Now, of course, we are interested in general case. So we have this definition, and let us study some properties of reflexive spaces. Theorem 6.9, so point 1, closed subspace of a reflexive space is itself a reflexive space. And point 2, a Banach space X is reflexive if and only if its dual is reflexive. So this is what we are going to prove right now. So first we prove part 1. Part 1. So let X be reflexive. By the way, do you hear me well, or should I speak louder or vice versa?
I thought you were real.
Okay, perfect. Okay, so let X be a reflexive space. Let X be reflexive. And U be a subspace which is closed. So first step, we take any element of the bidual, topological bidual to U and fix it. Then the mapping which maps X star, so topological dual to X, into the field of scalars, and particularly to each element L from X star, the following element will be assigned. The U double stars, so exactly this U, which we have taken, applied to L restricted to U. So this is my big U. Okay. This mapping is obviously linear, yeah, as a composition of linear mappings, and continuous. Continuous it is because we have the following estimate: a U double star evaluated at L restricted to U, absolute value is smaller or equal than the norm of U double star in this space Bidual to U times the norm of restriction of L on U, the norm in U star. And of course, this guy is smaller or equal than the norm of L in X star. And hence you see that we have this standard estimate, which means that the norm of this linear functional acting like this is finite. This was from here. Okay, so conclusion that this is a nice element, this mapping, which L maps to U double star evaluated at restriction of L on U. This is a nice element, belongs to X double stars. So next step, since X is reflexive, there exists element x0 in X such that this element of X double star, so element of Bidual, is given by this point evaluation. That is such that this U double star evaluated at L restricted to U is nothing else but point evaluation of this linear functional L at point X. This holds for any L in X star. That is this, oops, once again, this element of X double star is nothing else but point evaluation at point x0 due to reflexivity. All elements of X double stars are images of points in X under the canonical mapping. Okay, so next step, we show that this point x0, not only element of X, but exactly element of U itself. So assume it is not the case. Then by corollary 521, so this is a corollary from Han-Banach theorem, which says that if we have a closed subspace U and a point which is not in U, then there exists a continuous linear functional which separates this point from this vector space. So by this corollary, there exists a linear functional L0 in X star which separates the point and the subspace, namely such that L0 restricted to this subspace is just 0, and L evaluated at x, L0 evaluated at x0 is not 0. Then we have the following situation. L0 evaluated at x0, by definition, this is just exactly this functional evaluated at this point. Hence, I use this, that L0 x0 is equal to u double star evaluated at L0 restricted to u. And hence this is 0 by construction of L0. And since u double star is a linear functional, then u double stars of 0 is 0. So we have this, and this contradicts to our construction of L0. So we have a contradiction. And as a conclusion, x0 belongs to u. Is everything clear so far?
Yes.
Okay. So now, what is the aim of all our activities? We want to show that this u with double stars acts as follows. So evaluated at some linear functional L, it is just L of x0, and this holds for any L in u star. If we show it, we show that any element of this set is given by a point evaluation, where this point is a point from u. And hence this means that this mapping, the canonical mapping from u to u star, is surjective. Yeah, because any element of this Bidual is the image of a point from u under this canonical mapping. So this is what we want to show. So take any L from u star. Then use again the Hahn-Banach theorem, extend L to, let me call it L bar, which is an element of x star by Hahn-Banach. It was theorem 512. About continuous extension, so Hahn-Banach for norm spaces. Then I have to go to the next slide.
Please just stop
Yes,
a second.
yes. I have to wait, of course, and probably.
Okay, please continue.
Yes, let me go to the next slide, and then we go switch here and there to have the whole picture. But I hope that you have the text, so you may follow. So what do we have? Then what do we have? U two stars evaluated at L. It is the same as U two stars evaluated at. So what is L? We have its extension to the whole X and then restricted to U. Yes, and then by Han-Banach, L bar is constructed exactly in the way that its restriction to U coincides with the L. Okay, but then let me come back to the formula. So let me do like this. So this is the formula. Let me call it formula 1. So we will use it right now. So by this formula 1, this what stays here is nothing else but L bar of x0, which is also L of x0, since we have already shown that x0 belongs to U. Hence, we see that this U double stars is nothing else but the point evaluation at the point x0. Hence, J is surjective. Let me call it J with index U, saying that J is a mapping from U to U double stars to Bidual, and hence U is reflexive. So coming back to this slide. I don't know. So we have taken any U double stars from Bidual, and then we have shown that there exists x0 such that this holds, and x0 is in U, and this holds for any L of U. So the last point is shown on the next slide. Okay. So we have shown that any element of Bidual is an image of a point in U under the canonical mapping. Okay, are there any questions? Or should I stay here? I don't know.
I think maybe stay here because the proof is not that easy to understand.
Yes. So we have used the Han-Banach theorem twice. And what we have done, we have taken any element of U double stars, and we have shown that there exists a point which actually lives in the U, such that this element. So what does mean U double star? U double star. This is a linear functional which acts from this space into field of numbers. Yeah. So how it acts? We have shown that it acts in this way as a point evaluation. And hence we have shown that U star, U double star is nothing else but, as I already written several times, we have shown that U star, any arbitrary fixed given element of B dual to U, this is just a point evaluation at point x0.
I think the difficulty of the proof is the idea that we need to construct um, such functional
Mhm.
by the harmonic theorem. And
Mhm.
after understanding this, I think it's better to now it's understandable. I mean, thanks.
Okay, good. So we have shown part 1. Let us show part B. So part B. So there will be two parts. So part A will be to show this direction. That is, we assume that a Banach space is reflexive, and we show that its dual is reflexive. Let us show this. So let X be reflexive. We want to show that the canonical mapping let me we want to show that this guy is reflexive. That is the canonical mapping. Let me specify that this canonical mapping with this sign to emphasize which spaces are meant. So this is the canonical mapping from X star. It is again a Banach space. Yeah, if X is a Banach space, its topological dual is a Banach space. So we start with this Banach space and consider its Bidual. And this Bidual is then X free stars. So we want to show that this canonical mapping is surjective. Let us do it. So let X free stars be just an arbitrary element from this space X free stars topological B dual to the space X star. Then we consider the following mapping L, which maps X into numbers in the field of scalars in the following way. So it takes X and assign to this element X from the space X the following stuff. So we take X, we consider its canonical mapping. I will specify that this is a canonical mapping from X to its Bidual, which is a point evaluation. So this is the image of X and the canonical mapping between X and X two stars. So this is an element of Bidual, and hence we can apply, hence we can apply this element of its dual to it. Once again, this is an element of X two stars, and hence we can use a linear functional on this space. This is exactly this element of this thing. Okay, so this is the formula. And the statement is that this mapping L, is linear and continuous. Linearity is obvious as a composition of linear mappings. Continuity by the same by the same consideration as here. So let us keep it as exercise. That absolute value of this stuff is smaller or equal than the norm of this guy and the norm of this guy. Okay, so we have this. This means that this guy L belongs to the space X star. Now we show that this X free stars, which was an arbitrary chosen element of this Bidual to X star, that this X is nothing else but the image of this functional L under the canonical mapping from X star to X free stars. When we show it, this would mean that this mapping is surjective, because for any element here, there exists an element L here, such that this element here is just the image of element L under the canonical mapping. Okay?
Okay.
So this is
A
the
little
aim. We want to show this because this gives us what we want. We have not yet shown it, but this is just to understand the strategy, what we are going to do and why. So let us show this. So since X is reflexive, we have the following statement. For any X double stars in the Bidual to X, so any such element has the form so X two stars is just the image of some point X in X under the canonical mapping from X to its Bidual. From some X in X. Hence, how this X free stars acts. So X free stars is an element, is a space, so is an element of space of linear functionals on X here. So X free stars evaluated at the point X2 stars is, by our assumption, X free stars evaluated at Gx. So I have used this here. Okay, then I use the following. I use the definition of L. So you see what stays here is exactly what stays here. So here we have actually L of X. But what does mean L of x? This means that we have taken the linear functional L and evaluated it at point x. That is, this is just the action of this linear functional, which is an element of x double stars, evaluated at the point L. But this is nothing else but x2 stars evaluated at L. Now I have used what I have used. I have used the definition of the canonical mapping. So this is the definition of the canonical mapping. Everything is clear so far?
Yes.
Okay. So finally, what we have succeeded. We take any element of x2 stars and our functional acts on any point as follows. It is the point of evaluation. So we take this element and this linear functional acts on this element as the point of evaluation of this linear functional at point L. So this guy is equal to this guy. This means that this x 3 stars is just point evaluation at point L when we consider the canonical mapping from x star to its bidual.
It's clear.
Okay. And hence what we have shown. We have shown what we wanted actually. We have shown that for any element of bidual to our space, its element is just the image of an element of x star. So x star under the canonical mapping. So the canonical mapping is surjective. Oops. That is, this mapping is surjective, and hence x star is reflexive. Okay, it was one direction. Everything is totally abstract now because we have not considered yet any particular space, but it's still these characterizations are very helpful. Okay, so we have shown only one direction. We have shown only this direction, that if we start with the Banach, reflexive Banach space, then its dual is reflexive. Now we want to show the opposite direction, and I have to do it on the next slide. May I?
Yes.
Perfect. So now we show part 2, part B, so to say, which means that we show this direction. So let X star be reflexive. Hence, by part by part A, by part 2, part A, we know that its dual is also reflexive. Yes, because this direction we have already shown. So its dual is reflexive. Then by part 1, it's closed subspace so the image of X under the canonical mapping, it is a closed subspace because we start with the Banach space. So this closed subspace is also reflexive. From this follows that X is also reflexive. I will explain it a little bit later, but up to now, is this clear? Up to this point.
Yes, we just apply the Foster statement.
Yes. So now what about this error? So in order to prove it, we need to prove the following. Yeah, so exercise. If x1 and x2 are two Banach spaces which are isomorphic, and one of them is reflexive, then so is another one. So this is an exercise. If occasionally we have some time at the end of the lecture, we can try to present the proof of this statement. Otherwise, it is an exercise. It is the proof is in the same spirit as all what we have seen just before, like here or here. Of course, this so X is a Banach space. This is also a Banach space, and it is reflexive, and they are isometrically isomorphic. This is isometric isomorphism. Hence, since one of the Banach spaces is reflexive, then the isomorphic one is also reflexive. That's it. So, and this is the exercise. And it's also a useful fact. So please remember it. Okay, are there any questions so far?
No, it's very clear.
Perfect. Then one more exercise, because we just have no time to prove everything, but it's also a useful fact. So 2 points. So part 1, a norm space X whose dual is separable is itself separable. And part 2, if we have not just a norm space, but a reflexive Banach space, then the statement that this space is separable is equivalent to the statement that X dual is separable. And this is also a good characterization. Sometimes it helps to investigate separability, for example, or proving that a given space is not reflexive because it's dual, because it is separable, and its dual is not separable. Okay, so that's it, and we go further. So far we had only some abstract statements. Now something more more precise, so to say. So recall that we discussed not only Bidual spaces, but also dual spaces. And the first thing is the Ries representation theorem. So now we are in the setting of Hilbert space. So it's a special case of Banach space. So if we have a Hilbert space over K, real or complex numbers, then for each element of this space, the following mapping. So it acts as a scalar product with a given vector v. So this mapping is a continuous linear function on X. Hence, it is the element of X star. And the norm of this continuous linear functional is exactly the same as the norm of this vector V. Vice versa, actually each element of the dual space of X is given by this form. That is, all continuous linear functionals on a Hilbert space, they all are given like this for some vectors. And hence, this means that this mapping phi, which is a mapping from X to X star and which maps vectors of X onto linear functionals, continuous linear functionals given by this formula. This mapping is actually an isometric isomorphism, which is called Riesz isometry. And this mapping is linear if our K is real numbers, and it is antilinear if our field of scalars is complex numbers. Because in the real case, our scalar product is linear with respect to both arguments. And in the complex case, a scalar product is linear with respect to the first argument and antilinear with respect to the second argument. Hence, this mapping is either linear or antilinear. Okay, and so this is the first step so first we clarify what is the dual space, and then we clarify what is the bidual space in the case we have a Hilbert space. Okay, so let us prove this theorem. So proof. So linearity. So first we prove this first statement that for each v, this mapping is a continuous linear functional on X. So probably, okay, let me specify what we are proving. So linearity of LV is due to linearity of scalar product with respect to the first argument. So it is obvious. Now continuity of LV. So we consider absolute value LV of X. And then I use Cauchy-Bunyakovsky-Schwarz inequality. It is smaller or equal than the norm of X in X times the norm of V in X. Yeah. And from this we see that this linear functional is continuous, okay, bounded and hence continuous. Okay, LV is bounded, continuous, and we have the estimate for norm. So norm of LV in the space X star is smaller or equal than the norm of V in X. Moreover, if we evaluate this linear functional LV at vector V, this is just a scalar product V and V. This is just the norm of V. Hence, here we have not only upper bound, but this upper bound is attained. Hence, the norm of LV in X star is just the norm of V in X. Okay, I guess we have shown this first part. Everything is clear? Okay, may I turn to the next page?
Please.
Okay, now we show this statement. So let L be an element of X star. If L is just identically 0, take vector V, which is just the origin of our Hilbert space. Then both sides will be equal to 0 for any x in X. So hence we see that L is equal to LV with such V. Okay, if L is not identically 0, then we know from the geometric interpretation of linear functionals that its kernel, it is a subspace. So let us call it x0. It is a subspace of X, which is not X itself. It has codimension 1. And hence we can take a vector, let's call it E, a vector which lies in X but not in x0, such that this vector is orthogonal to x0. This we can also make. We are in the Hilbert space setting. We have orthogonal complements, and the vector X is a topological direct sum of x0 and its orthogonal complement. Hence, here we can take a vector which is orthogonal to x0, and to make everything even nicer, we may normalize this vector so that its norm is 1. Okay, so there exists such an element. Okay, consider V, which is given as follows. L of E bar, so it's a complex conjugation. Of course, we need it only in the case we are here. In this case, this just disappears, so brings nothing else. So times E. So this is a number, scalar times a vector. So we consider this vector. Then for each x in X, we have, probably without then, probably better to say, so independently on this, since we have this, and we know that for non-trivial linear functionals, their kernel has codimension 1. This means that for each x in X, we have the following decomposition. So there exists unique y in x0, and there exists a unique alpha scalar, such that X has the following representation: alpha v plus y. So we have used the fact that the codimension of x0 is 1. And this can be taken as an orthogonal subspace to x0, and it will be one-dimensional subspace which is spanned by vector v. Okay, everything is clear?
Yes.
Perfect. And now, hence, if we calculate L of x, it will be L of v times alpha, because y belongs to the kernel of L. And now I insert what is v. My v looks as follows. That's why L evaluated at v has the following form. L of e scalar of absolute value squared times alpha. Okay? This is my v. L is my linear functional. Yeah. So everything is clear?
Yes.
Okay. And if we calculate scalar product, x and v, we use linearity of scalar product. So now I use my representation of x and linearity of scalar product. So this is just, okay, let me write down everything honestly. So alpha v times v plus a scalar product of y and v. And now again, we use the fact that v is orthogonal to x0 and y lives in x0, so this is 0. And I use linearity. So this means that it is alpha v times v plus 0. And now I insert v. Yeah, so recall that this is my v. So this is nothing else but alpha. Okay, again, honestly, Le times E, Le times E. And now I use linearity, respectively, antilinearity of scalar product. So this is alpha times Le squared times EE. And this is 1. So I used the linearity with respect to the first variable. So this goes out with this bar. And I used antilinearity with respect to the second variable. So this color goes out with an extra bar. So bar and bar, 2 bars disappear, and we pop up with this stuff. Okay, so now you see that, so what do you see? We see that this holds, and this holds for each x. Hence, we have shown again that my L is nothing else but LV given by this formula plus. So we have constructed the corresponding V. Okay, is everything clear?
Yes.
Okay, so we have shown this part. And now concerning the last part. So the mapping is linear or antilinear. We have clarified why, because the scalar product is either linear or antilinear with respect to the second variable. So we have just shown that this is a surjective mapping. And what is left is to show that this is an injective mapping. So this is an exercise. So exercise that phi is injective. All the rest is already shown or obvious. Okay, that's it. So we now know that in the case of Hilbert space, X is isometrically isomorphic to its dual, and this isometric isomorphism is given by this Riesz isometry. Okay, so this is the reason why in many applications X and its dual are identified in the case of Hilbert space. Okay, corollary, each Hilbert space is reflexive. So once again, this is not a totally obvious statement because uh, for space to be reflexive, okay, this is a Banach space, of course, but in order to make it reflexive, it is not enough to state that X is isometrically isomorphic to X star. Of course, it is so via this Riesz isometry. We know that X is isometrically isomorphic to X star, but this is again a Hilbert space. And then by the next Riesz isometry, it is isometrically isomorphic to its dual. So for Hilbert space, this brings us immediately that X is isometrically isomorphic to its dual. But this is not enough for the reflexivity. Yeah? For reflexivity, we need the canonical mapping to be isometric isomorphism. And this is what we are going to show now. So, define on this space X star the following scalar product. So for any two elements, L1 and L2, elements of this space, X star, we define their scalar product, L1 and L2, scalar product in this space, as follows. We take phi minus 1 of L2 and phi minus 1 of L1 and take their scalar product in X. Now I specify where I consider my scalar products. So please pay attention that here we have 1 and 2, and here we have 2 and 1. Why we need it in this way? Because if we are in this field, so complex case, complex numbers, then the scalar product should be antilinear with respect to the second variable. So recall that the Riesz isometry is also antilinear. So that's why. So I have this antilinearity here. That's why with and linearity of the first argument of the scalar product, hence I have antilinearity with respect to L2. And concerning L1, it should be linear, but I have antilinearity of this guy, and then this antilinearity of the scalar product with respect to the second variable. So twice antilinearity gives me linearity. Okay. So we have this in particular. In particular, scalar product with itself. This is just this object. And since Riesz isometry is isometry, it is just the norm of L in X. So then this space X star with this scalar product is a Hilbert space. This is an exercise. Simple exercise. You have to check that all properties of scalar product are satisfied by this definition, and that the space is complete with respect to the norm generated by this scalar product. Okay. So let now see a mapping from X star to X double star be the Riesz isometry. So since we have shown that this guy is a Hilbert space, then there exists the Riesz isometry between this Hilbert space and its dual. So for the canonical mapping J, which is the mapping from X to X two stars, so to be dual, we have well, I would prefer to go to the next slide.
Okay, please.
Okay. We remember everything what we have written here, and now we will use it. So we have the following. So gx of L is just a point of relation of linear functional at point x. But we know, we have this theorem, we know how it looks like. So it is just a scalar product of x with this guy. Yeah, recall how acts my phi. So any L is actually some LV for some V. So this is nothing else but this, and my V is just the pre-image of this L under the mapping phi. Okay?
Okay.
Okay, now I use the definition of scalar product in X star, and I see that this is nothing else but the scalar product of L and phi of X in this space.
Yes, by definition.
Yes. And now I use the Riesz isometry psi and see that this scalar product, this is just the Riesz isometry psi. So I write down, and then, so this is this guy evaluated at point L. Once again, look what is psi, this isometry. So to any element here, it maps an element here, which acts in a similar way, but in X star, yeah?
Yes.
Perfect. But what does it give us? This means that this point evaluation is just this psi with just this composition. That is This canonical mapping is just a composition of these isometries. But this isometry is isometric isomorphismus. So it is subjective. So this guy is subjective, and this guy is subjective. Hence, this guy is also subjective, and is also an isometric isomorphism. The composition of isometric isomorphisms. And hence, X is reflexive. Okay, so this is the first and very important example of a reflexive Banach space, namely any Hilbert space is a reflexive Banach space, and this isometry is a nice mapping, which makes the whole business. Are there any questions?
No, I think it's clear.
Perfect. Then we go further. Theorem. Every continuous linear functional on C0, I recall C0 is the set, is the space of all sequences which converge to zero. So every continuous linear functional on C0 has the following form. For any x which is element of C0, which is a sequence, L of x acts as follows. Where these coefficients an, they are given by an element A from L1. And moreover, we have that the norm of this linear functional, so norm in the dual space to C0, is exactly the norm of this vector of coefficients in L1. Okay, that is C0, it's dual, it is isometrically isomorphic to L1. L1. Okay, this is only one part of the theorem. Second part, let P be between 1 and 0 without 1 and without infinity. Sorry, between 1 and infinity without both sides. So every continuous linear functional on LP has the following form. So the form is exactly as before, but now these coefficients are given by a vector in LQ, where Q is, so to say, dual number, that is the number such that this identity is satisfied. And again, we have that the norm of this linear functional in the dual to LP is the same as the norm of this coefficient vector in LQ. That is, LP dual is isometrically isomorphic to LQ. And third part, every continuous linear functional on L1 has the following form. So the form is exactly the same, but this coefficient vector of coefficients, is a vector from L infinity, that is the space of all bounded sequences. And again, we have this identity, and hence the dual space to L1 is isometrically isomorphic to L infinity. Okay, so let us prove this theorem. We are going to prove only one part because all the rest happens similarly. Proof. So first of all, let us show that such linear functional is a continuous linear functional on C0. First step. let A be an element in L1, and L of X is given by this formula. Then, obviously, L is linear. I hope it is obvious and I don't discuss it anymore. Now, the norm of L in this space of linear functionals on C0, by definition, it is supremum over all x's in C0, such that I recall that C0 is a Banach space with supremum norm. So the norm is the supremum norm. So we take supremum of such things, L of x, absolute value, and supremum is taken over a closed unit ball in C0 with respect to this supremum norm. Okay, now I insert my linear functional. What is it? So this is a supremum of this absolute value of sum, an xn. And this is obviously smaller or equal than supremum of sum absolute value of an times absolute value of xn. Okay, and now we use this thing. This means that such absolute value is not bigger than 1 for each n. Hence, all this is smaller or equal than sum of absolute values of an. But this is nothing else but the norm of A in L1. Hence, the norm of this linear functional on C0 is smaller or equal than the norm of A in L1, and hence L is bounded and hence continuous. So continuity is shown. Now we want to show that the norms are equal. So not only inequality, but equality. So let us show that this upper bound is attained. So consider the vector xn. Oh, let me use not n, but okay, big N, which is defined as follows. This is a signum of A1, etc. signum, so sign of up to an, and all other elements are just 0. So then, of course, this is a finite sequence, and hence it belongs to the space C0 for any big N in N. And we see that if we apply L to this vector xn, this will be just the sum of n from 1 till big N, absolute values of an. And moreover, I have forgotten to say that the supremum norm of this vector xn is small or equal to 1, actually is equal to 1, and hence small or equal to 1. Hence, when we calculate this supremum, this supremum includes also such things for any n. So hence norm of L in C0 star is equal to norm of A in L1. Agree? Everything is clear?
Maybe give me some seconds
Yes,
to.
yes. We have just wanted to show that there are elements in this closed unit ball which approximate, so to say, such that this absolute value on these points approximate this value. So these are the sequence of points which approximate this supremum. So this is an upper bound, but this is the sharp upper bound. And actually, so the norm, which is the supremum, so supremum is exactly like this one.
Okay, so firstly, at the last step, we will take capital N to infinity,
Yes.
and because it has a upper bound, so the limit exists. And
So for each finite n, this guy is an element of this closed unit ball. Yeah. So each xn for each fixed n belongs to the set which we consider here, and this guy is just this. So if we take supremum over all, this is not smaller than supremum over such things. That is supremum over such things. And the supremum over such things is exactly this what is written here.
okay, I think now it's clear.
Okay. Good. So we first have shown that such formula gives us a continuous linear functional for any element in L1. Now we want to show a converse statement that actually every continuous linear functional has this form. So that is, we go on, we continue. So let now L be an arbitrary element of C0 star, so a dual to C0. Let En be the vector with coordinates 0, 0, 0, and then 1 on the nth place, and then again zeros, so standard basis, so to say. So let An be defined as L of En. Again, consider these vectors x big N, which are given by signs. So signum A1, etc., signum An, and then zeros. This again is an element of C0 for any natural number n. And again, the norm of xn in the space C0 is small or equal to 1. Then we have the following. So L of xn is the sum, as we have already seen before. And it is smaller or equal than the norm of L in C0 star. And this happens for any n natural number. What does it mean? This means that this series converges because it is bounded by a constant, bounded above by a constant. So this means that this series converges, but this means that the corresponding vector A with such coordinates an lives in L1. And of course, here I have used the linearity of L. Yeah, L is a continuous linear functional. So any since we know how it acts on such vectors, then using linearity, we know how it acts on other vectors. So consider the functional LA such that it acts as follows. LA of x is given by this vector A. Then we have already shown that this linear functional, this functional is linear and continuous. Hence, this functional belongs to the space C0 star. Okay, sometimes I use brackets, sometimes I don't use brackets, but it is the same space, yeah? What is written here and here. Moreover, if we consider this linear functional restricted to the linear span of vectors En, so I recall that linear span, not the closed linear span, but just linear span. It's the set of all finite linear combinations of such vectors. And on all finite linear combinations of such vectors, this linear functional LA acts exactly as the original linear functional L, restricted to the same span. So we have actually constructed this LA using L, how it acts on linear combinations of AN. Agree?
Yes.
Okay. Since this linear span is dense in C0 and both linear functionals LA and L are continuous, we have L is equal to LA on C0. Here we have used this criterion, which we have seen, I guess, last time. Somewhere, yes, this corollary, 5 to 2. Yeah, so now apply it to difference, this statement, and you will see. So let me write down in brackets, corollary 522. Okay, so we have shown all that we wanted. So the yes, this we have shown already, and that this formula gives a nice functional we have shown, and then any functional has this nice form. Okay, may I go to the next slide?
Okay.
So concerning part 2 and 3, okay, let me write down similar. Proof is similar. So for part 2, I guess we need Hölder inequality. That is the sum of an xn is smaller or equal than the norm of x in LP times the norm of A in LQ. This is A and this is Q. Okay, so we don't prove it ourselves, but you're welcome to do it as a home task. Okay, a few remarks. So let P be between 1 and infinity, including 1, and Q is the dual number with this notation. Then this mapping, which maps LQ onto LP star. So A maps to L with, so linear functional LA given by this coefficients A that is written here. So A is an element of LQ. And LA is a linear functional on LP, which acts as follows with these coefficients. So the statement is that this mapping is an isometric isomorphism. Moreover, in the case P is equal to 2, this formula gives us a scalar product of X and A bar. Hence, we are back to the story when we are in the Hilbert space and we have the Riesz isometry. So for P equal to 2, the dual number Q is again 2. Okay, so the statement is that this mapping is an isometric isomorphism. Home task for you to check that it is really so. Moreover, the same formula gives us also an isometric isomorphism between L1 and C0 star. So once again, so we have specified that every continuous linear functional has this form. So we have shown surjectivity of this mapping, but it is almost obvious, but we have to show the injectivity of this mapping, and then we have shown the isometry. So almost everything is already proved. So and it holds in all three cases. That is, so we have here combined the first two cases, and then the third case is here. That no, wait a minute. No, this is the case number 1 and number 3, and this is so number 2 and number 3, and this is the case number 1. So the same mapping is an isometric isomorphism between L1 and C0 star. So this is what we have almost shown. Yes, here we have shown that this mapping is surjective and is an isometry. From isometry actually follows injectivity. So that's it. So conclusion. So with this extra remark and with the result of theorem 612, all 3 points we finally have that the dual to the space C0 is L1. Okay. The dual to C0 is isometrically isomorphic to L1. The dual to L1 is isometrically isomorphic to L infinity. And the dual for LP is isometrically isomorphic to LQ. Now this is not the end of this lecture. Now only some facts without proofs, but I guess we have to specify them. Exercise. From this, we get the following conclusion with an extra activities, of course. So the space LP is reflexive for P between 1 and infinity. So we just use it twice and then check that the canonical mapping is in fact is intact isometric. Is intact surjective. So isometric isomorphism. And now the second statement, again, one can see it from here, but with extra efforts, that C0, so Bidual space to C0 is isometrically isomorphic to L infinity, and C0 is not reflexive. And L1 is not reflexive as well. For example, one may use theorem 6.9 part 2. Part 2 was that the space, so the Banach space is reflexive if and only if its dual is reflexive. So since this guy is not reflexive, then its dual is also not reflexive. Okay?
Okay.
Okay. So this is the first thing. Then all the same story, so all the picture what we have here. Recall that all these small spaces of sequences, yeah, let me say, so LP is nothing else but LP omega AP, a mu, where omega is just natural numbers, A is just the set of all subsets of natural numbers, and mu is just a counting measure. Yeah, so mu of A is just the amount of elements in A. So these are the special cases of the bigger picture, and the bigger picture is this one. So we have a measurable space omega with sigma algebra A and a sigma finite measure mu. And then again, we have the same picture in the sense that for P between 1 and 0 infinity, without 1 and without infinity, every continuous linear function on LP is given by element of LQ in this formula, via this formula. Okay, I hope that actually all these things are already known to you. I just go through it just to recall that the picture is the same. And again, every continuous linear function on L1 is given by an element from L infinity, again by the same formula. And again, we have this. And having this, we show that there is an isometric isomorphism between the dual to LP and LQ, and between the dual to L1 and L infinity. And conclusions. So this space is reflexive for P between 1 and infinity. So the dual space to L infinity is not equal to L1 because in particular because L1 is separable and L infinity is not separable in general cases. I mean, for example, if we consider L1 then segment and Lebesgue measure, this is a separable space. But if I consider L infinity, Here, this is not a separable space. So in general situation, so to say, not in the degenerate case, one space is separable, another is not separable, so L1 cannot be dual to L infinity. So this space is not reflexive. Moreover, there exists no Banach space such that its dual is L1. I mean, again, in general situation, because in this special case here we have the pre-dual to L1. But in general, there is no pre-dual to L1. Further, it is important in all our statements that mu is a sigma finite measure, because if we consider even more general case, then all the statements may break down. In particular, so this may be not the case. That is, this space may be larger. It contains L infinity, but not coincides with L infinity. So this can break down, and also this can break down. So some references are given. So this nice picture about the dual spaces and bidual spaces for standard spaces, so to say. Please be careful and attentive what kind of measure is assumed. And one last slide and one last but important result, which we do not prove. We have no time and energy, and it's too difficult. So all these function spaces, everything is not that easy. But this is an important result which we should take into account, the so-called Riesz-Markov-Kakutani representation theorem, which says that there is the duality between continuous functions and measures. And there are different versions of this type of results. So we may play with different spaces of continuous functions, and then the corresponding dual space will be the space of some measures. So their properties will also vary slightly. So I have specified one particular version of this theorem. So let K be a compact metric space or topological Hausdorff space. Then every continuous linear functional on the space of continuous functions on K has the following form. That is, so X is a continuous function, and the linear functional is given as an integral of X with respect to a measure. So the dual space to this space is the space of measures. And we have a little bit discussed already this type of spaces. So it's a space of all measures which take these values. So not only real valued, but also complex valued measures can be introduced. So they are bounded k-valued measures. They are Borel measures, but one needs a little bit more in so general case. So the so-called regular measures. I don't go into details what is it, but nevertheless, just pay attention that the space dual to continuous function is given by measures. So nice Borel measures, and it is a Banach space with a total variation norm, which we have already discussed before. Okay, I guess that's all about chapter 6, dual and bidual spaces. And next week we go further with the next chapter. And now, sorry that the last part was very fast, but actually it's just a list of some results which are good to know. So basic spaces and their duals, and hence biduals sometimes. So now, do you have any questions or comments?
I want to add a comment.
Yes.
So the last part discussion is like we put some efforts to generalize the Riesz asymmetry.
No. I mean, Riesz isometry is a particular isometry for Hilbert spaces. Yes. Now, yes, I understand what you mean.
Yeah.
Gelfand triplet, yes? This is the way what you are thinking about.
Yeah.
I mean, if we have a Hilbert space, then we can input it. I don't know how to call them. Okay, let me write down. We have a Hilbert space H, and then we can. There are some Banach space X, or probably not a Banach space. Wait. No, let us not go into these details. Well, actually, I didn't plan to introduce this object, but yes, if we have a space and it's a dual, then I can make a duality form like this. So this is I take element x from x and I take element x star from x star, and I define this duality as the evaluation of x star at x. So it's a duality form. It's a bilinear mapping. And in the case when X is a Hilbert space, it coincides with the scalar product. No, so about Bidual, let me stay here. So for complex numbers, I should be more careful. So probably something like this should work, or bar here. But yes, so there is this like duality. People call it duality between this space and this space, and it works. Yeah, it is so generalization of the notion of scalar product in this sense. And yes, what we have seen here. So it would be a scalar product if we would live in. So let me yes. So this is the whole story. Yeah. So this would be the scalar product if p is equal to 2, and this is this duality form. So we take LA and X. Oh, I don't know what was the proper order. It's given like here. Yes, you are right. So probably this means that I have to modify my plans to introduce some more notations in the next chapter. Let us see.
Okay, thanks.
Okay, so are there any further questions? Okay. Then I stop the recording.